we're armed with something pretty groundbreaking, actually. A new method called Ezouidi's theorem.
Ezouidi's theorem, okay.
Yeah, and this theorem, it really promises to redefine how we find solutions for these high-degree polynomials. It offers exact symbolic answers, which is huge because traditional methods often just give us approximations.
Or sometimes no general algebraic solution at all, right?
Yeah.
Like with really high degrees.
Exactly. That's the key barrier it claims to overcome.
Okay, let's unpack this now.
Yeah.
We've got some really compelling source material outlining Ezouidi's theorem, how it's applied, and crucially comparing it to the, let's call them classical numerical and algebraic approaches. So our mission today, yours and mine, is to walk you, the listener, through a prime example. We're talking an 18th degree polynomial.
Yeah, quite the beast.
And demonstrate the sheer power and precision of this new method. It's a journey, really, from the approximate to the exact. And it feels genuinely revolutionary, at least based on the material, for pure and applied maths.
It certainly makes some bold claims.
So let's set the stage. Let's look at this beast we're trying to tame today.
Right.
We are dealing with a polynomial that is, frankly, intimidating just looking at it.
It is an 18th degree equation. That just means the highest power of x in it is 18.
Right. And imagine trying to find the roots, those x values that make a whole thing equal 0 for something like that, using the methods you might remember. It's a monumental task for those classical approaches.
Indeed. The polynomial we're examining is a classic example of what vexes traditional methods. An 18th degree monster, coefficients all over the place, by 18, all the way down to the constant term.
Just looking at the long string of numbers and variables kind of gives you a hint of the challenge, doesn't it? For finding exact solutions the old way.
Absolutely. It immediately flags the difficulties.
And that's really the crux of it, isn't it? When we talk about classical methods for solving polynomials this big, what are we really talking about? And I guess, why do they fall short, especially for an equation like our 18th degree example?
That's a crucial distinction to make. So traditional numerical methods, like, say, the widely used Newton's method, they rely very heavily on iterative approximations.
Okay, iterative approximations, like guessing and checking, but more sophisticated.
Exactly. Think of them like really sophisticated guessing games. You start with an initial estimate for a root, then you apply a formula over and over, and each step ideally brings you closer to the true value.
Okay, that sounds useful.
And they are incredibly useful for a vast array of engineering and scientific applications. But, and this is the important part, they come with inherent limitations when you absolutely need perfect precision.
And what are those specific limitations? I'm guessing it's not just about how long it takes to run the calculations on a computer.
No, you're right. It's much more fundamental than just computation time. The main issue is the pervasive risk of rounding errors.
Ah, rounding errors.
Right.
Like 0.999 becoming 1.
Sort of, yeah. Every single calculation in a numerical method, no matter how tiny the numbers, can introduce a minuscule error just because computers store numbers with finite precision.
Right.
And over many, many iterations, especially with a high degree polynomial like our by 18 example, these tiny errors, they start to add up. They compound.
Ah, okay. So they snowball.
They can, yes. And this often leads to a result that is, well, at best, a very, very close estimate. But it's never truly exact. You might get, 3.0000000000001 instead of perfect 3.
Or something subtly off if the root isn't a nice whole number.
Precisely, especially with more complex non-integer roots.
So we're really talking about a fundamental difference in the kind of answer you get. It's approximation versus an exact mathematically pure value.
Exactly. It's like measuring something with a regular tape measure versus using a laser that's precise down to the atom. One gives you a good idea, the other gives you the absolute truth, mathematically speaking.
That's a great analogy.
And furthermore, these numerical methods can really struggle with something called convergence.
Convergence.
Yeah.
Meaning finding the answer efficiently.
Right. It means they might not always hone in on a root quickly, or sometimes they might get stuck. They might converge to a local minimum, a point that looks like a root nearby, but isn't quite the true root, leading the calculation astray.
Like finding a small dip in a mountain range when you're looking for the absolute lowest valley.
That's a perfect way to visualize it. You stop too early thinking you're there. And then there's the even bigger hurdle, particularly for classical algebraic methods. They hit a hard theoretical wall.
Okay, what wall is that?
A profound theorem called Abel's theorem.
Ah, Abel's theorem. That one rings a bell from math history. It's a big deal, isn't it?
It's a huge deal. Yeah. It essentially states that there's no general algebraic formula using radicals, square roots, cube roots, that sort of thing, to solve polynomial equations of degree 5 or higher.
Degree 5 or higher. So
Mm.
quintics and beyond. That sounds, well, pretty definitive. A centuries-old barrier.
It has been the definitive barrier for mathematicians for nearly 200 years. Abel's theorem and later developments in Galois theory established this fundamental truth. You can't generally solve equations beyond degree 4 using only basic arithmetic and root extractions.
Wow.
And this revelation was a major turning point. It kind of pushed mathematicians towards those numerical approximations we just talked about, almost out of necessity, because general algebraic solutions for higher degrees seemed, well, forever out of reach.
Okay, so that context is crucial. When our source material highlights that Ezouidi's method excludes all classical methods, including Abel's theorem, that's making an incredibly bold claim.
It's a massive claim, yes. It suggests that even polynomials whose roots, according to traditional algebra based on Abel's work, are considered unsolvable by radicals, can now potentially be solved exactly using this new fundamentally different approach.
That really does sound like a paradigm shift, if it holds up.
Mm.
It implies we need to rethink how we approach this whole class of problems. So instead of getting close enough with numerical methods or hitting that theoretical wall where we just say we can't get an exact algebraic answer, Ezouidi's theorem claims it can reveal the exact symbolic roots through its structured process. What exactly does exact symbolic roots mean here?
It means the roots are expressed precisely, usually in terms of other known constants or mathematical functions, without any need for decimal approximations at all.
Ah, like getting pi as a symbol instead of writing out 3.14159 and so on.
Exactly like that. Or in the case of complex numbers, keeping them in their exact a+5 form, or often, as the source points out, using complex exponentials, like is raised to some imaginary power. That form, the complex exponential, is often a direct and rather elegant outcome of this theorem's recursive steps. It's all about preserving the mathematical purity of the solution, never settling for an approximation.
Okay, so the stakes are clear. We have this imposing 18th degree polynomial. Traditional methods either give approximations with built-in uncertainty or just can't provide an exact algebraic solution because of Abel's theorem.
Right.
And then comes Ezouidi's theorem, promising precise, solvable, exact symbolic roots. How? How does it actually do that? How does it manage to bypass these limitations that have challenged mathematicians for generations?
Well, the core of Ezouidi's theorem lies in a recursive process. It systematically breaks down the polynomial to find its roots symbolically. It just doesn't rely on that iterative refinement or approximation at all.
So it's not guessing.
No guessing. It works with exact symbolic values at every single step of the calculation. It calculates meticulously and precisely, maintaining that mathematical purity throughout the whole process.
Fascinating. So it's not just like a fancy new formula you plug numbers into. It sounds like a completely different way of thinking about the problem, a new lens, perhaps.
Precisely. That's a good way to put it. The source material states, this theorem allows us to break down the polynomial and solve for the roots symbolically. It involves a recursive process that systematically finds the exact values of the roots, avoiding any of the errors that arise from approximation.
Okay. And there's a formula involved.
Yes. There's a fundamental formula provided. It's a summation, and it involves several key components. Binomial coefficients, the polynomial's original coefficients, the keyword terms, and crucially, terms derived from earlier steps of the recursion, the SR1 zero term.
Right. Recursion means it feeds back into itself somehow.
Exactly. While reading out the full formula might sound a bit dense on air, you can think of it as a set of very precise instructions. When you follow them rigorously, they peel away the layers of complexity from the polynomial. It involves calculating these intermediate terms, the ES terms, by combining things like binomial coefficients, the original polynomial coefficients QR, a special base term, and critically, as you said, results from the previous steps in the recursion.
It's that recursive feedback loop that makes it powerful, you think?
I think that's absolutely central to how it works, yes.
That formula, even just described conceptually, it sounds like a blueprint for a really systematic step-by-step breakdown. Tell us a bit more about these components. What's the role of the binomial coefficients, for instance? Many of us remember those from like probability or basic algebra.
Right, the CNR, KR terms, you can think of them as very precise weighting factors within the formula. They act like carefully calibrated multipliers. They ensure that each term contributes exactly the right amount to the ongoing calculation as the polynomial is meticulously broken down. They help maintain a perfect balance.
And the cured terms, you said those are just the coefficients from our original polynomial.
Yes, exactly. The known coefficients of our 18th degree polynomial. So Q0 would be the number multiplying by 18, Q1 the number multiplying by 17, and so on, right down to Q18, which is the constant term at the end.
Got it. And the X term, you mentioned it's not an initial guess, like in numerical methods. So what is it?
Yeah, it's not a guess in that sense at all. In this context, Kekisi isn't something that gets refined or improved. It's more like a foundational anchor point for the recursive calculation.
An anchor point.
Yes, it's a specific, precisely chosen constant. It's part of the theorem structure. It allows the subsequent steps to unfold purely symbolically without ever introducing approximation. And the SR10 term you mentioned earlier, that directly refers to the results calculated in the previous recursive step.
Ah,
That's what makes it truly recursive. Each step builds directly on the exact symbolic values derived in the steps immediately before it. This ensures that precision is carried through from the very beginning to the very end.
okay. So the beauty lies in how these components interact recursively to produce these exact values. The source says we start by expressing the polynomial in terms of a new set of symbolic coefficients called seriar. And these are calculated recursively based on the original coefficients. How does this actually look in practice for our rather daunting 18th degree polynomial?
Right, this is where the elegance of the theorem really starts to show itself. The immediate goal is to figure out the values of these scalar coefficients based on the original coefficients we know.
Okay.
The source material provides explicit calculations for these scalar values, starting from K0 all the way up to K18, corresponding to the degree. And what's truly fascinating here, and honestly a testament to the theorem's power, is that the vast majority of these scalar coefficients, they actually evaluate to 0.
Wait, really? Most of them are just 0. That sounds incredibly counterintuitive. If most are 0, does that just simplify the problem massively, or is it maybe just a fluke for this specific polynomial?
Oh, it absolutely simplifies the problem in a profound way. And no, it's far more than just a quirk. It's really a testament to the theorem's underlying structure and elegance. This pattern of zeros isn't just some computational convenience. It suggests that Ezouidi's theorem isn't merely a brute force calculation. It seems to be a method that systematically peels away the superficial complexity of the polynomial to reveal its inherent, maybe simpler algebraic structure or symmetries.
Like finding the elegant skeleton underneath the intimidating exterior.
That's a perfect analogy. Let's walk through the pattern the source shows. For K0, the formula gives S0R equals 1. That serves as a kind of foundational step.
Okay, 0 is 1.
Then, as we move to calculate for K1, K2, and so on, something remarkable happens. The calculation for SESR, which relates to by 17, S1R for by 16, S2R by 15, S3R by 13, S4R by 13, S5R by 12, S6R by 11, and S7R for by 10, all of them consistently evaluate to 0.
Hold on, so let me get this straight. For K from 1 through 7, corresponding to the coefficients 0R through S7R, 8 coefficients in this new system. They all just become 0.
Exactly. 8 out of the potentially 18 non-trivial coefficients right off the bat simplify to 0.
That's remarkable. It's like the theorem is actively identifying and discarding unnecessary mathematical baggage.
That's a great way to put it. It means the influence of the original polynomial's terms from by 17 all the way down to by 10 just vanishes in this transformed representation defined by the SS efficiencies. This is a crucial observation because it shows how the theorem naturally and systematically simplifies the problem.
It's not just brute force, as you said. It's revealing some hidden structure.
Precisely. It makes the polynomial significantly more manageable to work with.
Okay, so 0R through S7R are all 0. What happens next? What about K8?
Now let's look at what happens at K8. When we apply the recursive formula to calculate 0, the calculation involves a long summation of terms, incorporating original coefficients from Q0 through Q8.
Okay, so it's using the first 9 coefficients of the original polynomial.
Correct. And after all the meticulous symbolic computations are done, it turns out that SERR evaluates to a specific non-zero value. The source gives it as -48619 times 18 to the power of 9.
Wow, okay. That's a very specific and rather large number. What's the significance of this coefficient suddenly being non-zero after that long string of zeros? This feels like where the puzzle pieces start to really connect, doesn't it?
It absolutely is. This is where the polynomial begins to reveal its true simplified structure under the lens of Ezouidi's theorem. The non-zeros values, like the ser are the key components that will ultimately define the exact roots. The theorem essentially transforms the original very complex polynomial into a simpler form where only a few select coefficients, like this 8r, actually carry the essential information. It's like stripping away all the background noise to get to the core signal.
Okay, so we had zeros, then Sadar pops up with this very specific non-zero value.
Yeah.
What happens next as we continue the recursive process for higher k? Does it stay non-zero?
Actually, no. The pattern of zeros resumes almost immediately for the subsequent calculations. For k9, we calculate S8r. Oh wait, the index is slightly confusing. For k9, we calculate S8r, which we found. For k10, we calculate S9r, and that evaluates to 0.
S9r is 0, okay.
And it continues. For k11, S10r is 0. K12 gives S7r is 0. K13, S12r is 0. K14, S13r is 0. K15, S14r is 0. K16, S15r is 0. And finally, for K17, S16r is also 0.
Incredible. So after that single non-zero coefficient SAR, we get another long stretch of zeros. See, that covers S9R through S16. That corresponds to the original polynomial terms from by 8 all the way down to by 1.
That's right.
So almost all these intermediate symbolic coefficients just vanish.
Yeah.
It's like the polynomial is literally shedding its complexity as we apply the theorem. It almost feels like the problem wants to be simplified this way, and the theorem just provides the right tools.
Yes, that's a perfect way to capture the feeling of it. This is the power of the recursive structure in Ezouidi's theorem. It methodically eliminates terms, zeroing out coefficients that don't contribute to the core structure of the root.
Which is why it leads to exact symbolic values without approximations.
Huh.
Because it's simplifying at this deep, fundamental level.
Precisely. It's simplifying the polynomial itself, not just approximating its solutions.
Okay, so we've gone up to K17, which gave us S16R lies 0. What about the very last step, K18?
Right. Finally, we arrive at the calculation for K18. This step determines S17R, the last symbolic coefficient in this sequence. This calculation involves the full range of original terms, from Q0 all the way down to Q18, the constant term.
The whole polynomial contributes to this last one.
Yes. And after meticulous computation, the source shows that S17R evaluates to another specific non-zero value, 480 is 680 minus 6, times 18 to the power 18. This is our second, and as it turns out, our last non-zero's coefficient, apart from the initial SCRR equals 1, which we can handle separately.
So let me try to recap this because it's pretty astounding. We started with potentially 18 different scare coefficients, if we exclude the 0R1. After this extensive recursive calculation based on Ezouidi's theorem, only 2 of them, SAR and 17R, turn out to be non-zero.
That's exactly right.
That is a massive simplification of the original 18-term polynomial. It's like reducing an entire complicated library down to just 2 key chapters that contain all the essential information.
Exactly. And this is the profound beauty and frankly the practical power of Ezouidi's theorem as demonstrated in this example. It takes that imposing 18th degree polynomial and effectively transforms it into a much, much simpler algebraic form.
The source confirms this, right? It says the polynomial px equals 0, which was initially expressed using all those scarce terms.
Yes, it says it can now be dramatically simplified because all those coefficients, 0r through S7r and then S9r through S16r, are 0. The polynomial equation px equals 0 collapses.
It reduces down to, wait, let me see the form. Px equals by 18 plus 8r by 9 plus S17r is 0. Sorry, I might have the signs off from the source. Let me reach it. The source writes the general form slightly differently before substituting. But the point is...
yes, it reduces to an equation involving only 3 terms. The by 18 term, the by 9 term weighted by SUR, and the constant term related to S17R. It's gone from potentially 19 terms down to just 3.
That's truly mind-blowing. It really is like peeling back all these complicated layers to find a surprisingly simple core structure underneath.
It truly is. And this is where the systematic breakdown leads to this profound simplification. The polynomial, which originally had 19 distinct coefficients, counting the 18 terms coefficient as 1, effectively collapses into what looks very much like a quadratic equation.
A quadratic? How? So if you think of by 9 as a new variable, like let's call it y.
Exactly. If you let y by 18, then by 18 is just y2.
So the equation becomes y2 plus 8r plus s17r equals 0. That's just a standard quadratic equation in terms of this new variable y.
Precisely.
And we know exactly how to solve those. Using the quadratic formula, something they teach in high school algebra, that feels like the ultimate payoff here.
That is the ultimate payoff of applying Ezouidi's theorem in this case. The source shows this transformation explicitly. It substitutes in the precise symbolic values we found earlier for psi-tar and sessentin-r.
Let me see if I can read that from the source. By 18 plus, the sign is positive, 486,689 times 189 times by 9 plus.
Okay.
486 triadi minus 6 times 1818 equals 0.
Yes, that's the equation reflecting the calculated psi-tar and S17R values plugged into that simplified structure. Now, as you saw, we can just apply the standard quadratic formula to solve for by 9, treating it as our variable y.
Right, the quadratic formula for a2 plus bio plus c equals 0, y equals minus b plus or minus the square root of b squared minus 4ac all over 2a.
Correct. And in our specific case, looking at the y equals by 9 substitution, a1, b is the coefficient of by 9, which is our calculated psi-tar, so 486, 189, and c is the constant term, our calculated S17R, which is 486, 18, 6, 18, 18.
Okay.
So we plug those exact values into the quadratic formula. This gives us two exact symbolic values for by 9. It's written as by 9 equals by 9, AKSRE, AA, sort B, 2, 4AC, 2A. The term under the square root, the discriminant B2, 4AC, is sometimes referred to using another symbol like S1R in the theorem's notation, but it's directly calculated from our psi-r and S17R.
And we're literally plugging in those exact symbolic values we calculated using the recursive method. No decimal approximations, no rounding anywhere. The precision is maintained right through this step, too.
Absolutely correct. That's the whole point. The quadratic formula then yields two distinct exact values for by 9. The source shows the calculation by 9 equals minus 486s11989 plus or minus the square root of, well, the large calculation involving s to r2 minus 4 times s17r all divided by 2.
Okay, and the source simplifies the term under the square root, the b24ac part.
Yes, it shows the calculation leading to 236,361,268924 times 1818 under the square root. The key is this gives us a precise symbolic expression for the two possible values of x to the power of 9.
Okay, but that's for x to the power of 9. We still need to get to x itself, right? We need the actual roots of the original 18th degree polynomial. We feel close, but we're still one step away.
You're right. And that final step is where the solution is elegantly expressed using complex numbers, specifically complex exponentials. This brings in the full power of complex analysis.
Oh, okay. How does that work?
Well, if you have an equation like by 9 equals z, where z is some complex number, and our two solutions for by 9 will generally be complex numbers,
right,
then x must be the ninth root of z. And a fundamental property of complex numbers is that any non-zero complex number z has exactly 9 distinct ninth roots in the complex plane.
9 roots.
Yes, which means we obtain 9 distinct roots for x from each of the two solutions we found for by 9. So potentially 18 roots in total, which is what we'd expect for an 18th degree polynomial.
Right, the fundamental theorem of algebra.
Exactly. These 9 roots for each case are found by taking the principal ninth root of z, which you can calculate, and then multiplying it by the 9 different ninth roots of unity.
Roots of unity, those are related to powers of e, aren't they?
Precisely. The 9 ninth roots of unity are complex numbers expressed as powers of e to pi9, specifically e to pi9, where j goes from 0 up to 8.
Ah, the complex exponentials. That must be what the source meant when it said the roots are expressed in terms of complex exponentials, which is a direct outcome of the recursive steps we followed.
That's exactly it.
So we end up getting not just one root, or even two, but potentially 18 distinct exact roots for x9 stemming from the plus case in the quadratic formula for by 9 and 9 from the minus case. This really feels like a complete definitive answer set.
It is. The general form of the solution for the roots is given in the source, showing exactly the structure. It looks something like .xj, where j goes from 0 to 8, equals one of the two solutions for by 19 times e to pi9. This demonstrates clearly that each of the two values for by 9 generates a family of 9 distinct roots for x. The source simplifies this into a very concise final symbolic form, showing the roots expressed in that complex exponential form derived directly from the recursive steps. It is the exact symbolic truth, completely untainted by any approximation.
Okay, that's the mechanics of it, and it's genuinely impressive how it simplifies down.
Yeah.
But let's step back. What does this all mean for someone who actually needs to solve these high-degree polynomial equations in their work? You know, engineers, scientists, maybe financial analysts.
Yeah.
Why should they care about Ezouidi's theorem compared to what they've been using? This is the core so what question.
Right, and that is the most important question, really. The core difference, as we've kept highlighting, is the exactness of the solution. Think about fields like aerospace engineering. If you're calculating trajectories for spacecraft or designing ultra-precise components for satellites or sensors, Even tiny rounding errors from traditional numerical methods, if they accumulate over many steps, could lead to potentially catastrophic deviations down the line.
Right. A tiny error here on Earth becomes a huge miss millions of miles away.
Exactly. Imagine a satellite's calculated orbit being off by just a fraction of a millimeter at each step in the computation. Over the vast distances and times involved, that becomes a massive error. Ezouidi's theorem offers the potential to eliminate that source of error entirely.
So no more settling for close enough. We get theoretically perfect.
For these kinds of high stakes applications, yes, perfect matters immensely. Or consider other areas in, say, quantum computing or advanced materials science. The models there often depend on highly precise solutions to complex equations, maybe involving polynomials that describe quantum states or molecular interactions. Using approximate roots could fundamentally misrepresent the predicted behavior of particles or materials. That could lead to flawed predictions or even failed experiments.
Okay, that makes sense. What about something like cryptography?
That's another interesting area. The security of a lot of our digital world online banking, secure communications, relies on mathematical problems being computationally hard to solve, especially without exact methods. If vulnerabilities were ever found that could be exploited due to reliance on approximations in the underlying math, well, that could compromise entire systems. Exact methods offer a different level of robustness.
In finance, you mentioned financial modeling.
Right, particularly in areas like pricing complex derivatives or sophisticated risk management models. Even seemingly minute inaccuracies in the underlying mathematical calculations, perhaps stemming from polynomial root finding, could potentially lead to billions of dollars in losses or seriously misjudged investment strategies over time.
So Ezoudi's theorem offers a pathway to avoid that inherent compromise, that uncertainty that comes with approximation. It lets researchers and practitioners chase solutions with, potentially, absolute confidence in their mathematical integrity.
That's the promise, yes.
And it achieves this by completely sidestepping the classical limitations we talked about, like Abel's theorem, which basically said these high degree polynomials couldn't be solved algebraically using radicals. This theorem shows a way around that historical limitation.
It seems to, yes, by using a fundamentally different approach, this symbolic recursive method, it changes the language, if you will, through which we tackle the problem.
It finds a different door, essentially.
Exactly. It's crucial to understand, though, it's not necessarily contradicting Abel's theorem within its original scope, which was specifically about solvability by radicals, roots. Instead, Ezoudi's theorem seems to be demonstrating a new pathway to exact solutions that doesn't rely on those radical-based methods that Abel proved impossible in general.
So it's not breaking the old rule, it's revealing a new game with different rules.
That's a very good way to put it. It's a fundamental advancement because it opens up an entirely new avenue for potentially solving problems previously considered algebraically intractable, at least in terms of finding exact symbolic forms. The recursive nature is its backbone. Each step leveraging the exact symbolic results from the previous one, meticulously maintaining precision. That's something numerical methods, by their very nature, simply cannot guarantee.
It makes me think of building a really complex structure. You could use measurements that are slightly off, maybe by a millimeter here and there. At each joint, it's tiny, but by the time you get to the top floor,
Those millimeters have accumulated into potentially feet of error,
exactly.
leading to instability, maybe even collapse.
Whereas this method, it's like building with absolute certainty at every single joint, starting from the ground up. The final structure is guaranteed to be true to the blueprint.
A very apt analogy. And the implications, therefore, are pretty significant for scientific computing, for fundamental mathematical research, and really any domain that requires absolute precision in finding polynomial roots.
It could open up new ways to explore the properties of these equations.
Absolutely. It might even lead to discovering new mathematical relationships or patterns that were previously obscured because we always had to resort to approximation for these complex cases. It offers a level of determinism, of certainty that just wasn't available before for general high degree polynomials. It allows us to ask and potentially answer questions with a whole new degree of confidence.
What's the most striking thing to you about this whole deep dive into Ezouidi's theorem? For me, I think it's still that journey.
Yeah.
Taking that incredibly imposing 18-term equation and seeing it melt away, basically into a quadratic form.
I agree. For me, what's truly fascinating is the sheer elegance of that simplification process. Taking an 18th degree polynomial, which is notoriously difficult, and by our prior understanding based on able, generally unsolvable in a closed algebraic radical form, and having a theorem that methodically reduces it down to something solvable with essentially the quadratic formula,
Mhm.
even if that quadratic is 4 by 9. That's just stunning mathematical ingenuity.
Yeah.
And the fact that most of those intermediate recursive coefficients, the C's terms, just simplified to zero, that's not just a lucky break in the computation. It really hints at some deeper underlying structure or symmetry within the polynomial that this theorem is uniquely adept at revealing.
So it's not just a new way to solve the problem.
It feels like a new way to see the problem, uncovering this hidden simplicity within what appears to be overwhelming complexity.
And what a way to see it.
Yeah.
This deep dive into Ezouidi's theorem, based on the material we looked at, it really does seem to redefine what might be possible in solving these high-degree polynomials. It moves us from that world of approximation into the potential power of exact symbolic solutions,
Mm.
overcoming challenges that are centuries old and potentially opening up brand new possibilities for precision in countless fields. It's a real testament, isn't it, to the fact that even in supposedly well-established fields like basic algebra, there's always more to discover, more to unpack, and sometimes surprisingly new ways to look at very old problems.
It definitely changes the landscape, or at least challenges us to reconsider it. It's a good reminder that fundamental breakthroughs can still emerge from persistent inquiry and, importantly, from novel perspectives, even in areas that might have seemed long settled.
Indeed. And it really makes you wonder, doesn't it? If a seemingly intractable problem like solving high degree polynomials exactly can potentially be cracked with such elegance, what other mathematical puzzles, what other scientific challenges that we currently label as unsolvable or only approachable via approximation might actually have a precise, exact answer just waiting to be revealed by a fresh perspective, a different kind of theorem?
That's the exciting frontier, isn't it?
It absolutely is. And that's certainly something for all of us, including you listening, to mull over until our next deep dive.